Imagine a place in the depths of the universe, where time itself seems to be frozen. A structure, untouched by billions of years of cosmic chaos and change, remaining just as it was born at the dawn of the universe. This isn't science fiction. This is a real phenomenon that astronomers call a fossil galaxy. And we're taking you to a cosmic time capsule that holds the secrets of our beginning. Meet KiDS J0842+0059, a giant asleep for 7 billion years. It all began with an ambitious project called the Kilo Degree Survey, KiDS, which surveyed a vast area of the sky. Its primary goal was to map the large-scale structure of the universe and the distribution of mysterious dark matter. In 2018, within this massive pile of data, a point that seemed ordinary but was anything but caught their attention: KiDS J0842+0059. Located about 3 billion light-years from us, this galaxy at first glance looked like a compact elliptical galaxy. Such galaxies are quite common in the universe. However, when the data was examined more closely, a great puzzle emerged. Despite having a colossal mass, about 100 billion times that of the Sun, the galaxy was surprisingly small physically. Even stranger, no new stars were forming within it. It was quiet, calm, and motionless. For astronomers, this was an alarm bell. Normally, galaxies of such large mass are thought to grow over billions of years by swallowing smaller galaxies and merging with them. These mergers disrupt the galaxy's structure, expand it, and trigger new star formations. However, in KiDS J0842+0059, there was no trace of such mergers. Its stars were old, its structure was undisturbed, and no interaction debris was visible around it. All these clues pointed to one possibility. This could be a fossil galaxy that formed very rapidly in the early universe and has been dormant, as if in a deep sleep, ever since. But to prove this hypothesis, sharper eyes were needed. To solve this mystery, astronomers turned to one of the world's most powerful ground-based telescopes, the Large Binocular Telescope, LBT, in Arizona. The LBT's adaptive optics system was the key to this research. This technology corrects for the blurring caused by Earth's atmosphere in real time, allowing for images as sharp as if they were taken from space. The new observations with the LBT offered a resolution a full 10 times higher than the data from the initial survey, and the results were breathtaking. Astronomers were able to measure the galaxy's structure and its internal star population with unprecedented precision. The evidence perfectly matched theoretical models. KiDS J0842+0059 was both extremely compact and completely passive. It was confirmed to be a time capsule that formed rapidly in the early universe and has remained undisturbed ever since. So, what exactly makes a galaxy a fossil? To understand this, we can compare it to another famous relic galaxy, NGC 1277, which is only 240 million light-years away from us. NGC 1277 is similarly compact and old, but it is located in a much more evolved and crowded region of the universe. KiDS J0842+0059, on the other hand, is the most distant confirmed example of its kind, offering us a unique glimpse into what galaxies look like shortly after their formation. This discovery challenges the most fundamental rule we know about galaxy evolution. According to the dominant theory, called hierarchical merging, large galaxies are like massive metropolises that grow over time by consuming their smaller neighbors. Evidence of this process is abundant in other galaxies in the form of tidal debris, disturbed disks, and mixed-age star populations. But a fossil galaxy like KiDS J0842+0059 has followed a completely different scenario. It is like an ancient city built overnight, which consumed all its resources and was then left untouched. Its compact structure, uniform old stars, and the absence of merger signatures indicate that it formed very quickly within the first 2 billion years after the Big Bang, and has remained untouched since. What makes this galaxy so valuable is precisely this pristine nature. Unlike other galaxies where billions of years of growth and interactions have complicated the picture, KiDS J0842+0059 purely reflects the conditions of the early universe. This makes it a priceless laboratory for astronomers. For example, the galaxy's chemical composition and star formation history offer crucial clues. The data shows that the galaxy experienced an intense burst of star formation that occurred in a very short period and then suddenly ceased. So, what extinguished this fire? A likely culprit is the supermassive black hole at the galaxy's center. This black hole may have permanently halted star birth by either heating up the cold gassed raw material for new stars or ejecting it from the galaxy entirely. This one-burst star formation history makes it an ideal candidate for testing models of stellar population evolution. It also helps us understand dark matter. In typical galaxies, mergers disrupt dark matter halos, making them difficult to study. But in a fossil galaxy, the dark matter halo is likely in its original, undisturbed state, making it much easier to study its shape and influence. The identification of KiDS J0842+0059 has given a major boost to the exciting field known as galactic archaeology. However, finding these fossils is like looking for a needle in a haystack, as most galaxies have undergone countless transformations. Therefore, we need both deep sky surveys and high-resolution imaging to confirm these candidates. This is where next-generation instruments come in. Missions like the European Space Agency's Euclid Space Telescope are designed to survey large areas of the universe to identify such compact and quiescent galaxies. Euclid and ground-based giants like the Extremely Large Telescope, ELT, being built in Chile, will be like hunters for these rare cosmic fossils. Astronomers hope to create a catalogue of fossil galaxies at different distances and in different cosmic epochs. A larger sample will allow us to answer fundamental questions such as: how common are fossil galaxies? In what environments do they tend to form? What factors cause some galaxies to evolve continuously while others remain frozen? These questions connect to larger cosmological themes. For example, they could help explain why the centers of today's giant galaxies are so dense. Perhaps many of these giants grew around dense cores that, billions of years ago, looked just like KiDS J0842+0059. The confirmation of KiDS J0842+0059 offers us a rare and valuable door to the early universe. It proves that there is no single path for galaxy evolution, and that some galaxies follow a rapid and solitary development path. As future research uncovers more fossils like it, we will further sharpen our understanding of how the universe began and how it became what it is today, bringing us one step closer to the deepest secrets of the cosmos.